Today we will see the how differentiation can be applied to draw graph of functions. Okay, so now if we are drawing, then we have something like this. So now the curve is bending in a particular way. Let us say for example like this, or it is bending like this. In this it is of this category, and here it is bending like this. Now, what is the difference of these two types of bending? Now, if we look at now, let us draw tangent at each point. As we can see that when the curve is bending like this, then the tangent, they are increasing, because these angles are getting bigger and bigger as we move further. Now, in this case, if I draw a tangent at this point and then I draw the tangent at this, and we draw a tangent at this. So, this let me draw it again. Now, if I draw like this, then I draw like this, then I draw somewhere here. As we can see, further we go, the tangents are decreasing. So, here f prime decreasing, and here f prime increasing. So, this we say that it is concave up, this is concave down. So, now define it formally. The graph of a differentiable function y equal to f of x is concave up on an interval, rather open interval I, if f prime is increasing on I, and concave down on an open interval if f prime is decreasing on I. So, we have also studied how to determine the function to be increasing on an interval or decreasing on an interval. So, what we had seen is that if it is a differentiable function, then if f prime is positive on an interval, then f is an increasing function. If f prime is negative, then on the interval, then f is a decreasing function. So, now if we assume here that our f is twice differentiable, then if f is twice differentiable, then f concave op on I if f double prime is greater than 0 on I and f concave down on I if f double prime is less than 0 on I. So, concave op sometimes you will write C u and C d for convenience. So, when f double prime is positive on an interval I, then f prime is increasing. Similarly, negative will imply f prime is decreasing. Now, there can let us see this. So, here as we can see that this is concave down and this is this one is concave up. So, there can happen that some graph like this can happen, where this is concave down and this one is concave up. From this point it is changing from concave up to concave down. So, those points where the curve changes its character in terms of the concavity, they are called point of inflection. So, definition: a point P on the curve is called an inflection point if f is continuous, there, that means f is continuous at that point P, and the curve changes its concavity from concave up to concave down or concave down to concave up. So, this is the point where for example, as we have seen. So, this is the point which is the point of inflection point, this point is called. Okay. Now, let us look at some concrete example. So, let us most familiar example which we have drawn at an early stage, f of x equal to x square. Now, this f prime of x, this is equal to 2 x. So, f prime is positive if x is greater than 0 and f prime is negative. Okay. So, we want to look at x is less than 0, but you see looking at f prime we can only say about the function is increasing or decreasing. Now, in order to check the concavity, we need to go to the second derivative. So, this is f double prime of x which is equal to 2, which is strictly bigger than 0. Thus, f is concave up or CU. So, therefore, if I want to draw this, this is an increasing function, this is a decreasing function on the negative side, and now the bending of the curve will look has to be concave up on both the sides. Similarly, if we look at f of x, this is equal to x cube, then you can see that f prime of x, this is equal to 3 x square, which is positive. That means, this is entirely this is an increasing function on entire real line. Now, f double prime of x, this is equal to 6 x, this is positive if x belongs to 0 infinity. Therefore, in 0 infinity this is concave upward. Now, if f x is negative, then this is minus infinity is 0. Therefore, on the negative side this is concave downward. So, here as you can see that point up to point minus infinity to 0, this is concave downward, and this is concave upward. So, here at 0 the curve is changing the nature concave down to concave up. So, 0 is inflection point. Whereas, here for x square 0 is not an inflection point, because throughout it is concave upward, but in f of x equal to x cube, definitely this is going 0 is a point inflection point. Now, let us we have a function such that f prime of x, this is positive on minus infinity to 1. That means, f is increasing in this interval, and f prime of x is less than 0 on 1 infinity, and f is also twice differentiable, which is given that f double prime of x, this is positive on minus infinity to minus 2 union 2 to infinity, and f double prime of x is less than 0 on minus 2 to 2 in this open interval. And also let us say that limit x goes to minus of infinity f of x, this is given to be minus of 2, and limit x goes to infinity f of x, this is equal to 0. So, now let us try to draw the curve tentatively how it is going to look like. So, this is 1, this is 2, this is minus 1, minus 2. Now, this is minus 2. Okay. So, f is a decreasing function on 1 infinity, and now on 1 infinity it is a decreasing function, and it goes to 0 as x goes to infinity, and on 1 infinity up to from 2 to infinity f double prime of x is positive. Therefore, this is going to be f prime is an increasing, this is concave up. So, here whatever the value it is going to take, this is going to be concave up, and which goes to infinity. Now, on minus 2 to infinity, and between 1 and 2, this is again a decreasing function because of this, and but in between 1 and 2 f double prime is negative. Therefore, f is going to be concave down, and here 2 is going to be inflection point. Now, from 1 to minus 2, 1 to minus 2, this is f double prime is negative, therefore, f is concave down. Now, from minus 2 onwards, f double prime is positive, f is concave up, and now limit x goes to minus infinity, this is going to be minus 2. So, this is concave up, and so this is tentative, this is what qualitatively this graph of this function will look like. And the point inflection point, definitely 2 is an inflection point. At 1, this is also changing. So, this is minus 2 to 2. So, minus 2 is an point of inflection, 1 is not, because on 1 to 2 this is f double prime is negative, this is throughout concave down. So, 1 is not a point of not inflection point, this is inflection point, this is also inflection point. So, this is whatever the value, this one is 2 f of 2 and this is minus 2 f of minus 2. So, these two are the inflection point of this curve. Okay. Now, one would like to know that what is the necessary condition for a point on the curve to be an inflection point. So, we can say that let us call it as a theorem, C f of C is an inflection point. Let then f double prime of C, this is equal to 0. The proof, let us assume, suppose this is CFC is an inflection point. Therefore, the behavior bending of the curve on the left hand side of C and the bending of nature of the bending of the curve on the right hand side of C, they will be different. Without any problem, we can assume that curve is concave down on C minus delta to C for some delta, and concave up on C to C plus delta. Okay, then what happens? Then this is this means f prime is decreasing, and f is twice differentiable. We need to assume that f prime is decreasing on C minus delta to C and f prime is increasing on C to C plus delta. So, and f is twice differentiable, therefore, f double prime of C will exist. This is equal to limit h goes to 0 plus f of C plus h minus f prime of C divided by h. Now, if h goes to 0 plus, then C plus h is bigger than C. Now, f prime is increasing, therefore, f prime of C plus H is greater than f prime of C. Therefore, numerator is a positive quantity and denominator is a positive quantity. So, this is definitely will be greater or equal to 0. Now, similarly, f double prime of C, because it exists, this is also equal to h goes to 0 minus f prime of C plus h minus of f prime of C divided by h. Now, in this case, as you can see, C plus h is less than C, and f prime is a decreasing function. Therefore, f prime of C plus h is greater than f prime of C. So, numerator is again a positive quantity. Now, denominator is negative h. So, therefore, the limit is going to be less or equal to 0. So, these two things will imply that f double prime of C is nothing but equal to 0. So, if C is CFC is an inflection point, then and f is twice differentiable, then f double prime of C is going to be 0. So, this is a necessary condition. This may not be a sufficient condition. So, if that means, if f is twice differentiable and f double prime of C is equal to 0, then may not be necessarily true that CFC is an inflection point. For example, converse may not be true. Consider the function f of x is equal to x to the power 4. Then f double prime of x, this is going to be 12 of x square. Now, f double prime of 0, this is equal to 0. Now, is 0 a point of inflection for this x to the power 4? So, now this is of course, on the right hand side this is going to be an increasing function, on the left hand side it is going to be decreasing function, and here f double prime of x, this is 0 if x positive is greater than 0 as well as x negative. So, therefore, f prime is an increasing function of x, therefore, this is going to be concave up in the entire domain. So, now, not necessarily true that if f double prime of C is equal to 0, then C f C is going to be a point of inflection. Now, then it is quite natural to ask that what is a sufficient condition for a point CFC, C comma f of C is to be a point of inflection. Well, if f is thrice differentiable and f double prime of C is equal to 0, then CFC is an inflection point okay, I will put it in this way. Let f is thrice differentiable, given that f double prime of C is equal to 0 and f triple prime of C is not equal to 0, then CFC is an inflection point. Well, so in order to show that, what we need to show is that at the point C on the left hand side and on the right hand side the concavity are different. Okay, f triple prime of C is not equal to 0. Assume either it is going to be positive or negative, assume f triple prime of C, this is less than 0. Now, what we know is that f triple prime of C, which is equal to limit h goes to 0 plus f double prime of C plus h minus of f double prime of C divided by h, which is equal to limit h goes to 0 plus f double prime of C plus h divided by h. Now, look at this, h is positive and this entire limit is less than 0. This is less than 0, that is what we are assuming. So, this will imply that f double prime of C plus h for small h, this is less than 0. So, this will imply that f prime is decreasing. Now, similarly, if I take f triple prime of C on limit h goes to 0 minus f double prime of C plus h by h, this will imply that f double prime of C plus h has to be positive, because this is a negative, denominator is negative, therefore, numerator has to be a positive quantity in order to get the limit to be negative. So, this implies that f prime is decreasing here on C to C plus delta, f prime is increasing on C minus delta to C. Therefore, FC hence CFC is an inflection point. Remark that point can be a point of inflection without f triple prime of C not equal to 0. So, which means look at f of x, this is equal to x to the power 5, then definitely f triple prime of 0 is equal to 0, but 0 for x to the power 5, you can see that 0 is going to be a point of inflection. Therefore, a point can be a point of inflection, still f triple prime of C is can be equal to 0, but what its sufficient condition says that if it is thrice differentiable, f double prime of C is equal to 0 and f triple prime of C is not equal to 0, then definitely C f C is going to be an inflection point. Thank you. So, we will continue with the behavior of the curve by using derivative. We will try to draw qualitative picture of curve in the next lecture. Thank you.